Hey, I'm Milind, the lead product developer at Molecular Quantum Solutions. So today we're going to dive into using our Python SDK and show you how you can access the Cebule engine from Python. If you go to our GitLab repo and you can scroll down to see a pip command to install the Python SDK in your environment. You'll also notice we have a bunch of notebooks and scripts to help you get started with the SDK. We're going to go into the notebooks and start with our quantum chemistry descriptor notebook. So first of all, you're going to want to fill out your .env file in either your home directory or current directory and put your MQS account credentials in this format there. We're then going to use the .env library with Python, and that's going to load your credentials into the OS environment, which we can then pass to the Cebule SDK to initialize your session. Once you've done that, you can start with the Cebule functionality. So you can call the tasks function, and that's going to give a list of all the tasks you've run with Cebule, the statuses, the results, and more information. We can also dive into individual tasks. So I've run a bunch of tasks beforehand for brevity, but here for running a new task, you're going to use the create task function. It's pretty similar across all tasks. You'll put the name of your task, the type, and some input for your task, and then followed by the number of processors you want to use. So here we're doing an atom order task, and what atom order tells us is a bunch of other tasks in Cebule are going to give us descriptors for a molecule that have information for each atom. Like maybe we get the optimized geometry of a molecule with the coordinate for each atom, and this is going to tell us which atom is in which order in those descriptors. So we can call wait for result once we've kicked off this task for the ethanol atom order, and then it's going to wait until the task finishes and give us the result. So here we see the atom order. Great. Now we can also run geometry optimization here. And what this is going to do is optimize the geometry of ethanol, first with a quick force field optimization, and then a more intensive semi-empirical method optimization using the GXDB method. And we can use 4 cores here. Once we kick off a task, we can also check its status via the task status function. Here it's new because it just started when I had run this task status. And again, we can call wait for result and see the output coordinates. So now we know that the third coordinate, for instance, is going to correspond to the third hydrogen in the atom order. We can also run a force field molecular dynamics descriptor calculation. And here, what's going to happen is we're trying to simulate if we have 10 copies of an ethanol molecule, our primary molecule, in a box with a saltwater solution that I've defined right here. And in the saltwater solution, I'm saying 1,000 copies of water and 30 copies of salt. And here I've defined it to run for 100,000 femtoseconds. If I wanted this to finish in like a few minutes, then I could just, make this 10,000 femtoseconds or just shorter time. And I'm going to use 4 cores here. So another way, instead of calling wait for result once you've kicked off a task, is you can use the wait for done function, which is just going to wait until the task finishes without giving the result. And then you can separately use get result to grab the result. And here we have the MD descriptor, which is going to be the average forces on each of the atoms in our primary molecule ethanol throughout the simulation after the system is equilibrated. Great. So we can also check our group contribution descriptors. And we have a few different methods for group contribution. We're just going to use one processor because it's a very quick calculation and do this for ethanol. This is going to give us the different functional groups if we split up the molecule into different groups. And it's also going to give us the volume and surface area parameters of these functional groups and the interaction parameters between the different functional groups. We can also run a Cosmo simulation where we're going to connect our geometry task, which means that we're going to initialize the Cosmo simulation of ethanol with the output coordinates that we optimized earlier. And here we're going to use DFT and configure a bunch of other parameters. Specifically, the dialect is going to set us to be using a water solvent, so essentially simulating the ethanol solute in a water solvent here. And we should use 64 cores here for the most efficiency because DFT is a very intensive calculation. And we're going to wait for the result and get the output surface charges. We can take this Cosmo result and stick it into a compact sigma profiles descriptor. And here we're going to connect the Cosmo task to a sigma calculation. Just use 1 core because it's really quick. And we're going to use the Cosmo RS model here which is going to give us both the sigma profile and some compact sigma moments descriptors, which we can see here in the output with the sigma moments and the sigma profile with the charge density as well. We can also run solubility calculations with Cebule, and this is going to involve computing sigma profiles with Cosmos SAC model for your solute and solvents. So here we're going to simulate benzoic acid in water. And first we're going to run the geometry optimization for benzoic acid, then the Cosmos simulation, and then we're going to do a sigma profile calculation. And here we're going to use the Cosmos SAC method, which we use for solubility. We're going to do the same for the solvent of water. And then we have both of their sigma profiles here. And we're going to take those sigma profiles and stick both of those tasks, the sigma tasks, into a solubility calculation. We're going to put the temperature to do the calculation at, and as well as some properties about our solute benzoic acid here. And then we're going to put an initial guess for the solubility value. And since we only have water solvent here, not multiple solvents, the composition of the solvent is just all water. And then we're going to get in the output here the solubility prediction and as a molar fraction, as well as the confidence. Great. So now that you know how to use the Cebule SDK to kick off quantum chemistry tasks and compute descriptors, you can also go to our documentation at docs.mqs.dk, and we have descriptive overviews of each task type and all the inputs and outputs that you can give. Have a great day.